well. One is that some of you already know a lot of the things that I will talk about, I suppose. And the second thing is I'm also very new to ecology. In fact, I don't know anything. Everything I know, I've learned here about swallows and tigers and everything. It was a very interesting couple of days. So I'll try to be brief and probably fail at that. All right, so the premise is that combining citizen science and AI can supercharge outcome for ecological monitoring, enhance cost efficiency, accuracy, and multi-sector engagement. I've read a bunch of papers making this claim, which is great, but the question is how. So we all know that AI is a very powerful tool, and we're talking here about, you know, classifying 500,000 photos and things like that, which are obviously not something that we want to or can do manually with limited budgets. And we do know that AI is pretty good at visual tasks, notably facial recognition, for instance. We've seen progress where in some contexts of some competitions, AI algorithms will actually do better than humans. But we also know that there are some very bad mistakes due to biased data sets and so on. We also know that AI is, it can make mistakes that seem kind of stupid sometimes, or at least to us humans. Here's an example from the Google Cloud Vision API. Supposedly they have pretty good algorithms. This is the famous duck rabbit, and what I wanted to show you here is just that by rotation, the classification changes as a function of the rotation angle. Sometimes it's recognized as a duck and sometimes as a rabbit. So this one may be particularly hard, but still it shows one type of or one category of errors that we might see in vision recognition algorithms. One common approach is that I've seen in a number of projects is ask the humans when the confidence level of the algorithm, the classifier, is below some threshold. It seems to be a common approach. There's one problem with that is that algorithms are sometimes wrong even when they are confident. So here's an example of a dog classified as a cat. Here's another example with more horrific results. Though I will tell you that the Tesla driver who was supposed to be monitoring his autopilot, in this case survived, though he was quite lucky. All right, so here's another thing. When people look at a picture, they can glean a lot of unstructured information, a lot of stuff that may not be in the data set. What's in this picture? What's the weather? What's the season? What are these kids doing? How are they feeling? What's their gender and age? All of these things kids can answer with good results. These are things that are harder for AI algorithms to answer. And the reason is we know our world, we have common sense, we have a lot of contextual knowledge that machines are lacking. So humans are still better at some things, acquiring and processing unstructured information, like in this case, learning from sparse data, which I'll show you in a second, recognizing unusual circumstances and their consequences, which is more important in prediction tasks, but can also be important in classification tasks. And again, flexibly combining multiple sources of information. Sometimes it's not just what's in the picture, but also some other things that we know about the season, about geographical information. Some of this may be coded as image metadata, but sometimes it's not. We're also able to see some patterns where machines won't be able. For instance, if it's a video, I'll just show you one here. Oh, sorry. Let's look just at one example, kind of a noisy example, but hopefully you can see a horse riding on the right. Seems like it'll be difficult for algorithms to notice that. Learning from sparse data, we can sometimes learn even from one example. For instance, if I show you this picture of fossils, and I tell you that the one in the red square is a tufa, just a name we came up with, or not we, the authors of the paper cited below. And I ask you to find the other tufas in this poster. So this is learning from one example. Now, if you look at it for a few seconds and you look at the one on the top left, you might say, yeah, these look like they should be in the same taxa or the same family. If you look at the one on the extreme right on the second row, also looks like one. So people, turns out in experiments that Tenenbaum and others have done, that people are indeed pretty good at this task. Of course, for machines, it's harder to learn from one example. So we can think of those more realistic environments as, I call them semi-structured, we can find other names for it, where there are certain characteristics of these environments. There are things that may be difficult to codify or quantify to put in training sets. Data may be sparse. For instance, in our context, some animals are only seen once. There are small training sets. And this is a point that Chuck Stewart brought up yesterday, small training sets, and there's a steady stream of images, new images, potentially showing new individuals, but sometimes showing the same individuals, and sometimes it's hard to know. Patterns are sometimes difficult to discern, or sometimes they don't exist. There may be sudden changes, and again, combining multiple sources of information may be helpful. So the hypothesis is that in those environments, and maybe it's not an exhaustive description of these environments, combining inputs from groups of people and computer agents can potentially yield classifications that are better than those that are created by either individual humans or individual algorithms or groups of either. Though, we don't want to throw all of our resources on every image. We have to keep cost benefit in mind as well. So we do want to use people where they need it the most, but maybe it's not so simple to know where it is, or maybe it is. We also know that people and algorithms err differently. I won't go into the details of this example for lack of time. So bottom line, the question is now, how can we innovate in this field? And I'll share some thoughts. Here's a regular reinforcement learning scenario. The autonomous car is seeing something, it suspects that it's a traffic light. This can be used for supervised learning, but also for reinforcement learning. And we humans tell the machine, yes, you're correct, or no, you're wrong. So in this regular scenario, people are helping the machines learn, whether it's supervised or reinforcement learning, which is good. But in biodiversity monitoring, it's not the main goal. One thought we had was mutual reinforcement learning. Machine learning needs a lot of example. Our data, as we said, is often sparse, so we need people to help. In order to do that, we want to make them better too. So one thing we can do is training the crowd. This is precedents in other crowd computing projects. IARPA folded, and I believe Kevin Croston told us yesterday also in LIGO. And this proves to work well. Helping people learn also helps promote their motivation and engagement, and providing them reason to remain active in those communities. Yes, we can use Mechanical Turk, but it's probably better to work with community members who are more engaged and more knowledgeable and more motivated to try to really classify things correctly. So who will help the people learn? Could be other people, could be the AI. So I'll just spend 1 or 2 minutes on some ideas we're considering, but really invite a discussion, because we're really just starting to think about things, and maybe some of these things are things that people here have done already, and maybe not, and maybe people have other ideas. One thing we can do, and this is inspired by Foldit, is provide people with visual scaffolds. For instance, if I am asked to classify some picture, and I could ask, show me similar images, meaning show me a bunch of images that the algorithm finds similar. Show me similar images taken in the same area and in the summer, same season, and etc. Show me the results of edge detection or things like that. Some kind of a playground to play with visual properties, play with color, play with lights. For instance, if we're trying to look at these pictures, I believe algorithms will find it a little bit hard to find the tigers here. Some people can find them easily, but then if we play a little bit with lighting, at least on the right picture, this makes things easier for people to see. Another important realization is that combining inputs is helpful. There's a lot of literature, both from the forecasting literature and from machine learning, about combining predictions or classifications from multiple algorithms, multiple humans. The sources of those classifications or predictions need to be independent, uncorrelated, with relevant knowledge of information. So there's a lot of work done on aggregation functions and mechanisms. But we think that beyond that, in the context of biodiversity monitoring, it's actually important to expose disagreements. That may be also important in other contexts, such as intelligence work. Instead of settling for combining through some averaging function or aggregation mechanism, we propose to further expose and highlight disagreements, because they are occasions for learning and improvement, and potentially also for new discoveries. Here is a sketch that Ofer did. Imagine that we're showing a person an image, and we're asking whether it's a dog or a jackal. And we can also show what other people, or maybe what other algorithms, have thought, and their confidence level of, or what percentage of the people thought it was this or it was that. We can also have all sorts of cues in the picture, like the size of the circle and the color of the circle might represent kind of the age of the tagging or other things. And maybe the red one is the one that's my prediction. So I'm thinking, 80% jackal, maybe 20% dog. Here's the orange one is where we really expose a disagreement. This one is sort of polar. There are some people or some algorithms that give it a very high confidence level for being a dog, and some that give it a very high confidence level for being a jackal. Maybe that's because a dog and a jackal mated and created something new, like a flying tiger. Okay, so it could be a potential for discovery. I didn't have a picture of a dog jackal, but finally, another idea is double loop learning, and the notion comes from organizational theory. I won't trouble you with that too much. What I want to say here is that I'm thinking of teaching the algorithm sort of second order. So going to the people and asking, well, why did you think that this was a dog, or why did you think that this was, not what we thought, and interviewing them or through some online forum or whatever, helping them tell us what the important features are. By doing that, and again, inspiration here comes from Foldit, where the community is highly engaged with the platform operators and the researchers. It's all one community. By keeping them deeply involved, members can actually make substantial contributions to the improvement of models over time. In summary, there's a lot of benefit from using machine learning, of course, first and foremost, scalability and speed. Yet facing the challenges of nature photography, bad lighting, sparsely populated data sets, imbalanced data sets, machine learning classifiers can and will fail. And so people can complement the models, also improve them over time. While doing so, they can also gain themselves. The question is, how do we do this? And we're still we have some research questions, but we're looking for more. Where can humans help the most? Do we know some specific species and ecological research questions that are more relevant, or people are more relevant, whereas others maybe, maybe the performance of algorithm is so good now that you really don't need humans. What tasks should humans do? Is it, Chuck Stewart again told us yesterday that people are better at comparisons than at classifications. But then when you do pairwise comparisons, there's an issue of, scalability. Trade-off, again, a point from Chuck yesterday, trade-off of accuracy versus completeness versus human effort. And eventually, boiling this down for the 45 minutes of discussions that we'll have in this group, what are some smaller, sensible, doable research questions, studies that we can do eventually to achieve these two goals, improve the quality of classifications, as well as enhance our understanding of how combining human and machine intelligence can help. Thank you very much.
All right, thank you very much.